Hi guys, today I want to talk to you about a very funny way and also useful way to drive a LED. So you basically have a lot of circuits, but the most used one are the classical low side NPN transistor with the resistor here and the LED, VCC and the transistor. This is RB, and the equation is you design IC, which is equal to beta times IB. You use this voltage here called VK, and this voltage here called VB. The current flowing to the base, IB, is equal to VK minus VB over RB. This project is basically consisting in designing the base current with the forced beta method, beta forced method. You suppose that in order to have the saturation region, you remember that the saturation region is characterized by VCE almost zero, yeah, 0.2 or 0.3 or something, and the beta which is less than 20, 8, 10, those can be numbers. The problem with this circuit, despite simple, is that when you change the LED, you change the drop voltage across it, and you are gonna change also the current flowing into the collector, because the base here is not clamped. The only way to do that is either to use circuit with a Zener on the base or to use another transistor. We will see then the second alternative, a little bit more complex, but feasible. You do have always a transistor with your LED here, your LED, optocoupler, whatever, but you use another transistor in this way, and you use a resistor R in this way. How does this circuit works? Yeah, then of course a base resistor RB. But this is not more important. How does this circuit works? Basically, the drop voltage, you make this resistor active, so you design the drop voltage of this resistor so that the collector of the transistor Q2 drains a little bit of the base current, and he will keep this current here constant. So the only equation useful is I, which is equal to VBE of Q2 over R. And no matter what LED you put here, no matter what load you put here, optocoupler, etc., the current will be always what you designed. This circuit is extremely useful, for instance, when you have to drive optocouplers and you want exactly 1 milliamp or 3 milliamp, something like that. So let's go on LTSPICE and let's see what happens. Here we are. So let's suppose that we use the VCC, which is the same for everyone, 5 volts. Easy to calculate, easy to do. And let's use the N2222 in every case. So let's suppose that I want to flow, let's suppose that in the first example, I want to make it flow a current ID equal to 10 milliamp inside this LED. And let's suppose that the VCC is 5 volts. I can suppose that the beta can be 10 because I want this transistor to operate in saturation region. And so I say that IC is equal to 10 times the IB. So IB is equal to 10 milliamp over 10. Yeah, it's extremely high. But don't worry, you won't have 1 milliamp anyway. It's called the beta forced method because then you redesign the beta according to the true value that you have. 1 milliamp is too much for a base current, of course. But now you put the resistor according to this. So RB is equal to 1 over 1 milliamp times 5 volt minus 0.7. So this becomes 1 kilo ohm times 4.2, which is equal to 4.2 kilo ohm. Okay? So let's use this one, 4.2 kilo ohm. And let's use, of course, now we need also to design the RC. And the RC, let's suppose a LED drop of 2 volts, because now I can design the RC. And why I can do that? Because now I am in saturation. And since I am in saturation, I can suppose this voltage equal to 0. It's not wrong to do that. So basically the circuit now becomes only this. 5 volts, the LED, and the resistor. This has a drop voltage of 2 volts and 10 milliampere flowing by design. So what is the RC? I have basically 3 volts here and I have to make it flow 10 milliamps. So V is equal to R times I, and so R is equal to 3 volts over 10 milliamp, which is equal to 3 over 1 milliamp times 1 over 10. So it is equal to 3 kilo ohm over 10. So it is equal to 300 ohms. So VCC equal to 5 volts, RB equal to 4.2 kilo ohm, VLED equal to 2 volts, and RC equal to 300 ohm. Now on paper this design what does tell me? That if I put 4.2 kilo ohm here and I put 300 ohms, I will have 10 milliamps flowing here. That is the meaning, the physical meaning of this design, which I did even without a calculator because it was very, very simple. Okay. As you can see, the design is long, and in reality it probably won't be like this. So now you have to make another iteration and other iteration to get the precise current. But anyway, let's put this on LTSPICE. So now I can put the LED, LED. Let's put this, and let's put 300 ohms. Let's put this guy to ground, and let's run the simulation. 1 millisecond, don't care. You see, I have 1 milliamp and 7.6 milliamp. So, the design was not entirely wrong, as you can see. Now I have IB and I have also IC here. So we can calculate the beta, the final beta, which is the true beta. So my beta now is IC over IB. So this is beta true, and the true beta is IC over IB. So IC over IB of Q1, and the value is 7.6. The value is 7.5. So now you have to do the reiteration again. You have to start over again with beta equal to 7.5. You start over again the reiteration. You should make an Excel tool with the iteration like this, and you recalculate again your RB. So let's do at least one. So let's do the second loop design. So now we have again the beta, which I suppose it was 10. Now let's start again with. I will do quickly. So I see. So beta first. I suppose that beta was equal to 10. IB equal to 10 milliamp over 10. So you see IB is equal to 10 milliamp over not 10 this time, but 7.5. Now I have to take the calculator. So it is 10 over 7.5. You see it is 1.3 milliamp. It is a little bit different. So now let's check at the base. The base is 0.731. So again, let's recalculate RB. So RB is equal to 1 over 1.3 milliamp times 5 volt minus 0.737. So you have 5 minus 0.737. It is equal to 4.2, 63 over 1.3 milliamp over 1.3. So I have 3.2, 3.28 kilo ohm. And now again I have now I should restudy the drop voltage of the LED, blah blah blah. But guys, okay, you got the picture. You got the picture. So it's an iterative method, and you get the picture. So you should lower again 3.28k. Oh, 3.28k, and the current will increase. You see, now I have 1.3 milliamp as a base current, and I have yes, I have to. Oh yes, sorry, because I have to recalculate RC again. Yeah, I have to recalculate RC. Sorry, RC is equal to again. Yes, you have to calculate RC and everything all over again. So this method is basically goes until you find a steady point on whatever you want to reach. But it is imprecise, and if you change, and not only that, but if you change the funny thing is that if you change the LED, of this, the current is gonna also change because it changed the drop voltage. For instance, let's put this and let's run simulation. Hey, you see, the current has changed. Yeah, the current has changed. The base current remains the same, but the current has changed because it has changed the drop voltage. So all this effort for nothing because you won't get a precise current anyway. So this method is useful if you want to drive a LED and you just want to turn it on. So you don't care of how much current you want. We can say that this method has a precise of 20 to 30% and we don't care. But if you want to drive an optocoupler or something very important with exactly 1 milliamp, you cannot afford to do all this stuff here. No. You have to do something more precise. Let me show it to you. So, let's use this guy again. And let's use the other transistor connected in this way. Let's use the same voltage. And let's use now just a diode. And now let's put exactly the resistor. So I want exactly 1 milliamp. So let's design VB is equal to 0.737, and the current that I want I load is equal to 1 milliamp. So the resistor R, V equal to R times I, is equal to 1 over 1 milliamp times VB. So it is 1 kilo ohm times 0.737, which is equal to 737 ohms. So let's put 737 ohms and let's close everything here. Now I should have exactly I should have exactly 1 million flowing. Yeah, as you can see, I don't have exactly 1 million. There is a little bit of discrepancy, but because let me check the drop voltage here. It's 60. Okay, so let's lower it a bit. 65.8. Okay. Okay, now I have exactly 1 milliamp. And no matter how I change this, I could even put two of them, you know. Yeah, I could do that. You see? Naturally, I have to increase a little bit the voltage because the two lights require a little bit more. But you see? You see? I even changed the voltage and I still have 1 milliamp flowing inside this branch. It's amazing how this circuit works so well. Naturally, if I scale down with one unit, I will have the milliamp, but it is quite obvious. I couldn't even have, I couldn't even I couldn't have really even four of them, and I will still have the milliamp. Nah, okay, of course I need a bit more voltage because each of these diodes has a drop voltage. So at least let me give at least 15 volt. You see? With 50 volts, I can drive 10 LEDs with 10 milliamp optocouplers. So you can do whatever you want with this circuit. But this one, oh, this one has changed. Yeah. So this one is resistor base dependent, collector resistance dependent. Yeah, you see? I changed the collector resistor, it has changed everything. And change the voltage, change the base resistor, change the collector, change the device, everything change everything here. But here, you just need to know the base voltage and this resistor. That's it. This resistor has no meaning. It's just to limit the base current, and that's it. So, let's summarize what we understood. Circuit only use, so the circuit is useful only when you have to turn on a LED without a precise current. Because it is RB dependent, beta dependent, Temperature dependent. RC dependent. VCC dependent. LED dependent. Some of you can say, ah, no, it is RC, it is RB dependent, it is VCC dependent because you connected the base current with the VCC, which you basically did this, and most of transistors don't have this connection. Yeah, true, true. Most of transistor driving have just 5 volts here, you know, from the microcontroller. That is true. So you could keep constant the base current, true, but it is still IB dependent. So it is not a good circuit. It is a good circuit only if you need to know this LED, and that's it. If you need to put a precise current, so this is a precise current sink. And therefore decides the current. And the question is I equal to VB 0.7 over R. You see? Very simple. That's it, guys. I hope that I didn't bore you so much. Okay? And okay. So, hope that you enjoyed this content and see you in the next video.